All right, welcome back to IDIS 343. Now this is where we start putting some real math behind our inventory decisions. On the menu, classifying inventories, why firms hold stock, the characteristics of inventory systems, and then the big one for today, the economic order quantity model, the EOQ. Later, we'll also extend it to a finite production rate and to an all units quantity discount. But the heart of all of it is EOQ, and that's where we'll spend our energy today. Now, here's the thing about EOQ. It's the simplest and the most fundamental inventory model we've got. Basically, it captures a trade-off between fixed ordering cost and inventory holding cost. Every time you place an order, there's a fixed cost which pushes you toward ordering larger quantities. For example, if fixed ordering cost is $100 and you buy only one item, then you have to charge that entire $100 to a single item. If you buy 20 items together, then $100 will be divided among 20 items. So share will be $5 per item. So that means larger the order quantity, the less is the per item cost amount coming from the fixed ordering cost of capital K. On the other hand, the larger the order quantity, the larger will be the inventory holding cost. So inventory holding cost forces us to buy smaller quantities. EOQ just finds the sweet spot where the total cost of fixed ordering cost plus inventory holding cost is minimized. And here's a little history. This model dates all the way back to 1915 to an engineer named Ford Harris. It's basically the grandfather of every inventory model that came after it. Every fancier system you'll meet later builds on this one. Every clean model rests on a set of assumptions, and EOQ has four. First, demand is known and constant. We call that rate lambda, units per unit time, and that unit of time can be weeks, months, or years, whatever fits. Second, no shortages allowed. That means we have to satisfy all demands. Third, there's no order lead time, so as soon as we order the product, we receive it, and we'll relax that one later and work with lead time as well. And fourth, the costs. A setup costs K every time we order, a per unit cost C, and a holding cost H per unit time. Now, keep your eye on that H. It does a lot of work for us, and it ties straight back to an inventory holding rate where H equals IC. Alright, picture the inventory level over time. A shipment arrives and the level jumps straight up to Q. Then demand eats away at it at a steady rate. That's the downward slope minus lambda. It slides on down to 0, and right at 0, the next order lands and we jump back to Q over and over. That's the sawtooth you see on the slide. Now, the length of one cycle we call T, and our whole goal, the thing we're actually solving for, is the Q that minimizes the average cost per unit time. Let's build that cost up piece by piece. Total cost is annual order cost plus annual holding cost, and for now, we'll set the penalty cost aside. In each cycle, the order cost is C of Q equals K plus CQ. And to turn that into an annual number, we just divide by the cycle length T. Well, how long is a cycle? T equals Q over lambda. You bring in Q units and burn through them at rate lambda. For example, stock 100 units with demand of 20 a day, and T is 100 over 25 days between orders. Now, the holding side. Annual holding cost is just the holding cost, H times your average inventory. And here's where that sawtooth really pays off. Because inventory falls in a straight line from Q down to 0, the average level across the cycle is simply Q over 2. Picture it like a triangle. The average height is half the peak, and our annual holding cost works out to H times Q over 2. All right, let's snap the pieces together. The average annual cost equals K times lambda over Q plus lambda C plus HQ over 2. 3 terms, and each tells a little story. K lambda over Q is the annual setup cost, and notice it shrinks as Q grows. Lambda C is the annual purchase cost, basically just paying for what you sell. And HQ over 2 is the annual holding cost. That one grows as Q grows. One term pulling down, one pulling up. And that tension right there is the whole game. Now, if you plot G of Q, you can actually see the trade-off play out. The setup curve, K lambda over Q, drops off fast as Q increases. the holding curve HQ over 2 climbs in a straight line. And if you add them up, you get a U-shaped curve. High on the left because, well, you're ordering constantly. High on the right because you're drowning in inventory, with a nice low point in the middle. And that low point, you know, that's the Q we're after. Now, how do we find that bottom? Calculus. We take the derivative of G of Q with respect to Q, and that gives G prime of Q equals minus K lambda over Q squared plus H over 2. Quick sanity check. The second derivative is 2K lambda over Q cubed, always positive for a positive Q, which means the curve really is convex, a genuine minimum. Alright, set that first derivative to 0, shuffle the terms around, and you land on Q squared equals 2K lambda over H. Take the square root, and there it is. Q star equals the square root of 2K lambda over H, and that right there is the economic order quantity. Now, a couple of things worth noticing. First, Q star lands exactly where the setup curve and the holding curve cross, or in other words, where they are equal to each other. And that's actually a coincidence, not a general rule, but you know, it's a handy mental picture. Second, and students always ask this, the per unit cost C isn't in the formula. Well, why not? The purchase term lambda C doesn't depend on Q at all, and when we optimize, it just drops right out. But don't think C is irrelevant. It sneaks back in through H because H equals IC. I mean, a pricier item costs more to keep on the shelf, so a higher C gives a higher H, and that does move Q star. Alright, let's see a numerical example. Number 2 pencils at the campus bookstore sell at a steady 60 a week. They cost the store 2 cents each. Ordering costs $12 and holding is based on a 25% annual interest rate. First, get everything onto the same time unit. Demand is currently per week and we can convert it to year. Annual demand lambda is 60 times 52, which is 3,120 pencil a year. The holding cost H is the interest rate times the item cost, 0.25 times 0.02, which is 0.005. Drop that into the formula and Q star comes out to 3,870 pencils. The time between orders T is 3,870 over 3,120, about 1.24 years. And the holding and setup costs, well, both land on the same number, right around $9.68. Now here's the insight the textbook flags. Notice the selling price 15 cents never showed up in the math. We'd order the same amount whether a pencil sold for 15 cents or $2 because, you know, demand is assumed steady no matter the price. Now for my favorite part. What if the bookstore just ignored the formula and ordered in round batches? Well, order 2,000 at a time and the average annual cost runs about $86.12. Order 4,000 and it's $81.76, and the optimal at 3,870, $81.74. Look at that, bumping up to 4,130 units past the optimum costs you a grand total of 2 cents, right? But cutting down to 2,000, roughly half the EOQ, well, that one actually stings. And the lesson is that G of Q is remarkably insensitive to errors in Q near the bottom of the curve. You really don't have to use the exact EOQ, get into the neighborhood and you're fine. So when your supplier says we cannot sell you 3,870 pen, you need to buy either 2,000 or 4,000. You can choose 4,000 without worrying about the high cost. All right. That's the EOQ model and our foundation of inventory management. Thanks and gig 'em.